Let me read Fred's bio that he gave me. Fred Best has been part of SSEC for 40 years, and for nearly 20 of those, he served with Hank on Hank's SSEC leadership team as technical director. Throughout the years, he has worked on projects with Hank in several capacities, as an engineer, as a program manager, and as a co-investigator. The projects include the HIS, the net flux radiometer for Galileo Jupiter entry probe, the ARI and the marine ARI, the scanning HIS, GIFs, and the CLARREO IR prototype, which is a topic of today's talk. Fred is truly grateful to have worked closely with Hank for all these years. It has been gratifying, rewarding, and most of all, it has been a lot of fun. Fred's talk title is the IR Absolute Interferometer ARI Technologies for On-Orbit Verification and Test.
Thank you, Bob. So this is a follow-on to what Joe was talking about, and I want to acknowledge the many people that are part of this effort that went into what I'm going to present here. In many ways, the ARI, which is the Absolute Radiance Interferometer, is a culmination of everything we've learned about FTS instruments and their calibration, starting with the HIS, going to the ARI, scanning HIS, and GIFs. And no other group has successfully demonstrated this 0.1 K3 sigma performance that Joe just described. What were Hank's contributions to this? Well, he formulated the climate benchmark mission that was selected by the decadal survey. That's a nice start. He defined the instrument and the calibration approach, and he led the instrument development and presided over its successful outcome. Well, I'm going to talk today about the on-orbit verification and test system, which is an independent check on orbit of the performance of the calibrated FTS that Joe just talked about. And the heart of that is the on-orbit absolute radiance standard that contains a system to set the temperature scale and a way to measure emissivity on orbit. Those are the two parameters that fix the amount of radiance that's coming out of the system. And then as Joe introduced the subject of the quantum cascade laser used to measure monochromatic emissivity and instrument line shape. And then I'll talk a little bit about recent work and then how we use all of these tools in the box to actually do an end-to-end verification on orbit. Hank presented this yesterday, and it represents sort of where we were up until the point where we started all this CLARREO work, where you do ground-based calibration of your instrument that goes to orbit with standards that are traceable to NIST. But once you're on orbit, there's nothing you can do anymore. You're basically relying on the fact that things don't drift. You can do periodic checks with a ground-based validation, but that's periodic. Sometimes it's very difficult to apply what you would learn in this validation to making any corrections up there. So this is kind of how things were done in the past, and if you just take the calibrated FTS without the things that I'm talking about, that's where you are. And Joe presented this. What we end up doing in that old way of doing business is you take the Earth scene and you calibrate it on orbit by looking at space for a 0 radiance reference and then an onboard, typically an ambient black body. However, now with the concept of CLARREO, you have an on-orbit independent verification system that's recognized, traceable to NIST standards. So you carry it with you. And one of the hallmarks of the climate benchmark mission is it's an imperative that you have this on-orbit capability. So I'm going to talk now about what the system is comprised of, and the main feature is what's called it's an independent radiance source called the on-orbit absolute radiance standard. It can be run at several different temperatures to check system linearity and as an absolute check on how well your calibrated interferometer is making its measurements. And the features of the ores are, the two significant are, one, it contains 3 independent phase change cells containing gallium, water, and mercury, which we use, we determine their melt points and measure their melt points on orbit to set a temperature scale. And I'm sorry about that. Okay, so we use those to establish a temperature scale. And the other thing that we have to do is we have to be able to measure emissivity. And for that, we use this heated halo. So I'm going to be talking to you, describing how the melt point system works and how we make that emissivity measurement. And that emissivity measurement is a spectral emissivity that comes from actually the measurements from the Michelson interferometer. Okay, so the on-orbit absolute radiance standard. First of all, we start with how good does it have to be, and why does it have to be this good? And we have in order to look at that, we have a calibration model that tells us what the calibration performance is going to be depending on the values of certain parameters in the system and their uncertainty. So of key importance are the blackbody references and the ores itself, what temperature, which spans a range of temperatures. And those uncertainties are 45 millikelvin 3 sigma, and I'll go through how, I'll loop on that number later in the talk. And the other key parameters are emissivity of the black bodies at 0.999 with a 0.06% uncertainty. If we can have our black bodies and our on-orbit absolute radiance standard to these accuracy values and uncertainties, then we can make the end-to-end 0.1 K 3 sigma measurement. We can verify that measurement on orbit with this system. Joe showed this slide up, so I won't go through it other than to just say that when you take all those parameters and plug them into the calibration model at various wave numbers, you can see that the combined uncertainty between the calibrated FTS and our independent verification system is under our 0.1 K 3 sigma. A little description now of what that on-orbit absolute radiance standard looks like. So its main feature is a aluminum cavity that's painted black and has a light trapping geometry. And then embedded in this cavity are temperature sensors and these 3 different phase change cells. And we also have out in front of it something called the heated halo, which allows us to do the emissivity measurement. So I will discuss that with you later. So just a little bit of a blow up. Here's our thermistor temperature sensors. They're embedded in custom housings. And the phase change cells are in similar housings in a welded assembly. And we're talking only 30 millikelvin of phase change material. It's a very small amount of material. I wanted to point out this fact that Larry was going through the Pioneer Venus small probe net flux radiometer in his movie yesterday. The black body light trapping geometry that we use today is the same one developed by Hank and Larry. Their black bodies that they used on the ground to test their end-to-end performance. And indeed, those very black bodies from the 70s were used in the demonstration of the very first ARI when Henry's group lent us the interferometer, we took those black bodies and showed that we can do what we want, and that was the birth of the ARIs. And then that same geometry has carried through the scanning his and ARI instruments and also the GIFs. So every single time we build a new instrument, even though it's the quote-unquote same black body, we learn how to make improvements in their performance and in the calibration process. Okay, so how do we do this temperature business? And this is illustrated on a curve, which is temperature versus time. And this is a heated cavity with a thermistor in it. So this trace here is the temperature that would be reported by that thermistor. And we take this cavity and go into a constant temperature right under the melt point of gallium. And when we process, we apply, we go into a constant power mode. We just give it a little shot of power, which makes us exponentially rise to a new equilibrium temperature. But that's what would happen. But if you put even a little bit of gallium in this system, something different happens. When you approach the melt temperature of the gallium, that power goes into changing the phase of that gallium, and it puts a kink in this exponential curve. Then it climbs out and reaches the equilibrium temperature. And so this is the signal that we're looking for that tells us we're melting gallium. And one of the things that happens here is the longer you take to go through the melt, the closer you approach the actual temperature of the theoretical melt temperature of the gallium. And this is really just a representation of the thermal gradients in the system. And when you go through everything very slowly, there's low gradients. So that's demonstrated over here. Every one of these data points is a data taken from one of these traces through a melt. And they fill out something that we call a characteristic curve. And this is the time it took to go through the melt, and this is the temperature that we would say it's melting at. And you can see it asymptotically approaches the actual melt point. Now, so one of the things about this is this characteristic curve is an invariant for any physical system. So we made time for accuracy, but once you have this established, you don't have to take 9,000 seconds to go through a melt. You can go here, and then there's a well-established fudge factor, so you don't have to spend all that time dedicated to this calibration. If you want to be convinced that you're on this characteristic curve at any time, have at it. You can always go back and do it. And then, as I said, we're establishing a scale from over a temperature range. So we have mercury at -39, we have water at 0, we have gallium at 29. We go through the same process, and the melt plateaus, we can establish the melt temperature to within 5 millikelvin, 3 sigma. And the process, because it's done slowly, there's very low gradients in the system, something on the order of 2 millikelvin. So we know that what happens here can be tracked here within this 2 millikelvin uncertainty. And because we have 3 temperatures, and when we go through these melts, when we go through each melt, we measure the resistance of each thermistor at that temperature. So then we have 3 equations and 3 unknowns to fill in a traditional relationship for thermistor temperature sensors. It's called the Steinhardt and Hart relationship. And so we can develop calibration coefficients for each of those sensors with those going through the 3 different melts. And some of the work that was done under the IIP at Wisconsin had to do with material compatibility to make sure that we weren't contaminating the melt temperature, because if you get contaminants in there, well, you can change its melt point. We don't want that. There's zero-G effects that squirrely things might happen and change the thermal behavior when you got on orbit. Sealing techniques to make sure that you didn't over time. And mechanical stress issues because water and gallium expand when they freeze. And you're constantly working the housing, which could put cracks into the housing. And the 2 metals, if they got into a cracked housing, would lose structural integrity via liquid metal embrittlement. So all of these things were looked at. We went through a rigorous test program where we did high temperature soaks at high temperature, cycles, deep cycles to do all the stress working, and we simulated at 7 on orbit. And what we did is, I want to just say the bulk of this work is carried out by Doug Adler and Claire Pedersen. And this just gives you an idea of how we were assessing that we were not doing anything bad in our accelerated life test. So here's the characteristic curve again, and then before we went into that series of tests, it's the solid lines that represent different melts, and the open circles are afterwards. So you can see that, you know, we're within 5 millikelvin. And this is for water, typically what we saw, and mercury. So we feel that we have a very robust way of getting this calibration on orbit to within 5 millikelvin. And this just shows the hardware pieces that make up this ORS, and that was all integrated together. During our thermal vacuum test of the system, this just shows a 24-hour period, the stability of the black body, and there are gradients in the system, but they're on the order of 15 millikelvin. The important thing is that we account for the effective temperature. We can assess an effective temperature of this radiance standard by putting different weighting factors on those thermistors based on Monte Carlo ray tracing methods and an understanding of how the optical system is actually viewing the black body. And one of the important things of all of this work is to be able to state our uncertainty. And so we spent a lot of time binning up the various contributions and assessing the uncertainty. And you can see that we're rolling up to 45 millikelvin 3 sigma here. That's the number that we had plugged in the beginning to say this is what we need to do our 0.1K 3 sigma job. And okay, so now I want to talk a little bit about the measurement of emissivity. Remember, there's two things: temperature scale, but we also have to measure the emissivity of this absolute standard. And this is the work that was led by John Jarrow during our instrument incubator program. So typically, you know, our FTS would view the black body like this. We have, for our ORs, we have a heated out in front, which is basically just sits there all the time unless you want to make this emissivity measurement. When you want to make the measurement, you turn on the heater to this cone segment here. And so then this sensor is seeing a signal from this elevated temperature reflection. And you can write an equation for the radiance being measured by this sensor, which is the Planck radiance from the black body temperature times the emissivity. Oops, I got to burn this baby out. Times 1 minus the emissivity of everything else, which is a view factor that the cavity has to the cone, plus 1 minus that view factor times the background. So basically, everything in this equation is known. But there was one problem, and that is that our electric detector has a very, 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 very low signal for this measurement. And so we have to integrate over a long period of time, which means we can't let the instrument deviate in temperature or it would just wash away the signal. So as Bob pointed out yesterday, we have a problem, and then we have a solution, which is to think about this in terms of writing the equation like this. You can solve for this emissivity, but you calculate the emissivity once every time you calibrate the instrument. And so then you're averaging calibrated measurements over time. You do not require this instrument to have stability over the multiple hours it takes to get this within the uncertainty you need. So that was a key to making this work. And this would be the result that we would get. So spectral emissivity as measured by the calibrated FTS. And because we have always used the same geometry of black bodies, we have a big history working with NIST and different NIST facilities. And there's overlaid on here several different of those measurements. And everything has been very consistent with each other and with some modeling that we've done also. So the one thing I want to point out here now is this drops off significantly here. and we want to be out to 50 microns. We want to be having a much higher emissivity out there. It's really the limitation of the paint that we use, and I'll just describe later what we're doing about that. Okay, so Joe introduced this. Harvard put together this quantum cascade laser, which enables 2 different measurements in our on-orbit verification. So we had a spectral emissivity that I just described. This one allows the emissivity of our black bodies to be made at the wavelength of the laser, and also to measure the instrument line shape. And this is a side view of the front end of our system, and that's a 45-degree mirror, and there's our interferometer back end. We inject this laser into our scene mirror, and it points, I don't know, it doesn't exactly look right, does it? We can point it into this black body, and then it gets viewed by the interferometer. We can point it into an integrating sphere to do the instrument line shape measurement. And this just gives you an idea of what the output looks like. We can get that emissivity of our ambient black body. We can illuminate the integrating sphere to get the instrument line shape. The other thing that we can do, by the way, is point to, Joe talked about the ordinate points, the 90 degrees. We can point off at 45 degrees to characterize any polarization issues we might have, even though we've designed the instrument to be immune to polarization. Okay, here's some recent work that we've done. We've been paid by Langley to close out a few details. So our paint kind of looks like this. And we have, there's been some work done at NASA Langley that showed that if you dope the paint with various nanomaterials, that you can enhance its emissivity. And so we are working to put in graphene nanoplatelets and getting our emissivity down here. Now, if we do that for the paint, the enhancement of the cavity puts us where we need to be to get that high emissivity all the way out to 50 microns. And the other thing, I think Joe really showed this, but we're getting our feet wet on what kind of expected measurements we're getting by injecting the laser into our black bodies in our integrating sphere. And we will soon be putting it into a flight-like configuration, so we'll feel more comfortable with what that ends up being, having done all this previous work here. Okay, I guess I'm going to finish up by just we got all these tools in the toolbox. How do we use them on orbit? And so all the different measurements that we can make absolute radiance verification with the ores. We can check calibrated FTS linearity. We can measure spectral emissivity from 3 to 50 microns. We can do this monochromatic emissivity with the QCL. And make that measurement of our ambient black body. We can do the instrument line shape. We also have a way to look at stray light issues by putting heated apertures wherever our beam looks outside the instrument. And that'll give us a signal to tell us that, hey, you're viewing something you don't want to be viewing, and then the polarization. So you can think of, there's 2 different time scales of how this, so over 2 minutes, this is a calibration cycle. So it continuously collects interferograms every 5 seconds, and the scene mirror is used to sequence through Earth, space, ambient black body, and then a view to this on-orbit verification and test system. And then that view to this on-orbit verification and test system can be mixed and matched. You could have different radiance levels, but the idea is that it always fits into the cycle, but it could be a different thing that you're looking at. So with that, this picture you've seen several times. It's basically, the instrument is on the aircraft. Our instrument, there's a laser that comes out of the instrument, the metrology laser, and that's kind of used as a fiducial mark for where we're pointing. And so what they're looking at is, where is the instrument pointing? And it sounds simple, but it can get complicated. And Bob pointed out yesterday that there was a big problem where the instrument wasn't looking where it was supposed to. And that's why you see this. And there's a lot of pictures of various ones of us looking, making sure we're looking where we're supposed to be looking. Okay, well, that's it.
So before we take some questions for Fred, there's a couple of things I want to say. One is, usually when we're looking down to see it, there's a laser beam coming up. Okay, keep that in mind. So that's one issue. The other is that I think the teaming between Hank and Fred is one of the most amazing ones that I've ever seen, because we wouldn't be achieving this level of accuracy without Fred's work on all these projects. We're talking about achieving temperature measurements in a radiative to a level of accuracy that when we somewhat naively took these to NIST to show them, they say, can we use that as our reference? You know, it's a big deal. They defer to Fred for a lot of this. So getting this sort of technology into space has been developed. It's done now. It just needs to get up there and be used for a lot of different projects. So it's a really, something I think that'll last over generations once it's become more accepted. So, any questions about? I want to add one thing to that.
Fundamental idea of establishing the temperature scale on orbit, not in the laboratory and depending on stability, is Fred's brainchild. The idea that you can do that with this less than a gram of material, quite a lot less than a gram of material, and put it in a significant sized black body and detect the signature is not all that intuitive. And you know, you just really need incredibly good control of the temperature electronically. And a lot of people have contributed to that, but it was Fred's brainchild for sure that made that possible. It's been a great development.
Well, somebody had to come up with telling me what was important, Hank.
Someone had to find the problems for Hank to solve. Any other questions?
Fred, what is your history, or how did you get started working with Hank back in the day?
Well, when I was hired by Vern Sumi, I was hired to be part of the engineering team. We were doing something with astronomy, which was we were building one of the first 5 instruments for Hubble telescope. And so that was my first job, mechanical engineer on that. And then with Wilt's group, that was my next instrument, the diffuse X-ray spectrometer, which was a dedicated shuttle payload. And that established a great relationship with space physics, which continues today. And then I guess, well, actually, it's kind of interesting because right around then, I was working on Hubble, DXS, and then Hank goes, well, by the way, Smith wants, we got this aircraft instrument we got to build. And we had so much work going on at Space Science that every machine shop on campus was saturated with our work. And there was like 5 or 6 machine shops around town. We were just cranking stuff. And it was fun. But that's kind of how I got started. They got an instrument in the door and they had to get it built. And there wasn't any variation in the delivery date. Bill.
So, you know, Fred and all, I find it very interesting. One of the quotes that I believe you've attributed to Vern is, the enemy of the good is the better, yet you keep making things better. So how does this jive with what you were brought up with?
Well, I don't make better than it can be, for one thing, and that's another feature of working with Hank. He'll keep you from doing that. he won't let you attempt something that's impossible. But, you do have to always be doing something better. Otherwise, you won't have any fun.
All right, well, thank you,
Well, thank
Fred.
you, Bob.